welcome to the fifth chapter of the tutorial. And in this chapter, we will learn about how to use multiple regression using STEM. And there are two cases when we add more than one predictors in a regression model. It will either be a continuous variable or can be a categorical variable. And in this chapter, we will learn about how to treat them efficiently in STEM. Also, when we have more than one predictors in our model, it's more complicated to interpret the posterior result. We will learn about more different plots to help us understand the posterior better. Let's start by adding continuous variables. Following our textbook, we use the WAFL divorce data, and we are going to investigate the relationship between marriage rate and marriage age, marriage rate, the divorce rate. Before going into the model, we first have to standardize our data. And I use the function called scale to standardize the data. But notice that the output of the scale function will be a matrix, and we cannot store a matrix in a data frame. So we have to use the bracket function to select the first column so we can get a vector. We will try three different models to see the difference between them. The first two models are simple linear regression models, while the third model is the multiple regression model with two continuous variables. Let's write down the STEM model for model 3, and the code for model 2 and model 1 are just a simplified version of model 3. The data block is very simple. We have a number of rows, median age of marriage, marriage rate, and divorce rate. The parameters block is also very simple. We have the intercept alpha and the coefficient for age, which is beta A, and coefficient for marriage rate, beta M, and sigma for the error term. We first need to declare our vector mu, which is equal to alpha plus beta A times median age plus beta M times marriage rate. And we have the sampling statement that divorce will follow the normal distribution with mean equal to mu and standard deviation equal to the sigma. And then we can declare the prior distributions. For alpha, since we have already standardized all the x, so we expect the intercept to be 0, so it will be normal 0 and 0.2. For beta M and beta A, we set both to follow a normal 0 and 0.5. For sigma, we set it to follow an exponential distribution to make sure the values are positive. In the generated quantities block, as usual, we need to calculate the prediction mu value and prediction y value. The prediction mu value will be the mu here, and the prediction y value values will be drawn from the normal RNG function. After completing model 3, we can pass the result to model 1 and model 2 with very small modifications like deleting the marriage rate in model 1 or deleting the marriage age at model 2, and we can have all three models. In the tutorial video, I want to focus on the interpretation of posterior distribution. The first type of plot introduced by the author was the predictor residual plots. Personally, I think this plot is the hardest to understand one in this tutorial. The intuition of this plot is like this. Let's say if we have 5 predictor, or we can say 5x, and if we want to know the impact of 1x on y, what can we do? So we can regress all the other x on the x we are interested in. So we will have a new regression model with the interested x on the left and the other x on the right. And then we can calculate the residual of this regression model. These residuals of the model can be interpreted as the effect of this only one x, while all the other x are controlled. And the third step is just to regress the y on the residuals we got from the previous regression model. So in this case, we have two x, age and marriage rate. So our first step is to, if we are interested in age, we have to regress, use age as y and marriage as x, and then calculate the residuals of age in this model, and then use these residuals as x and the divorce rate as y to do another regression. The models we use here is actually a very simple linear regression model with one x and one y. Only different thing is that in the generated quantities block, we add a new line to store the information of residual. And the calculation of residual is very simple. It's just the y value minus the mu value we predict. By fitting different data we can have the results we want. So in the residual A and model, age will be Y, and for the residual marriage rate model, marriage rate will be Y. We can use the s.data.frame function as before to extract the samples of the residual output from the generated quantities block. With these predictor residual values, we again need to do another regression model using divorce rate as y and this residual age or residual marriage rate as x. But I don't want to use Stan to do the regression again. I just use the building regression line function in ggplot. So what I did here is just to plot the point of the predictor residual and the divorce rate value, and then use the geometric smooth function. And with a method equal to lm, this line will do the regression for us. The output of the plot will be like this. Okay, so you can see the regression line here drawn by the geometric smooth plot. And then I do the same thing for residual m, and I plot the two results together using the grid arrange function. From the result, you can see that the impact on divorce rate is very small for marriage rate, while the marriage age has a larger impact on the divorce rate. The problem of the predictor residual plot is that the concept is very complicated and the process are also complicated. We need to build two regression model and to have our result. The second kind of plot we are going to learn is the counterfactual plot. More intuitively, counterfactual plot is very similar to what-if analysis. We are wondering how x2 will impact y if we set the x1 value to a certain constant. So for example, we can set age to be 0 and marriage rate to be from -3 to +3 with 50 points between this range. Don't forget that we've already scaled our data, so age equal to 0 will be the mean value, and the marriage rate will cover most of our data. Besides, our model needs to be modified a little bit. I want to calculate the counterfactual plot for age and marriage rate at the same time. So firstly, I add these data to the data block, 50 points of age and marriage rate. Like the counterfactual points for age and marriage rate at the generated quantities block. But notice that we have to declare the values we want to calculate in the generated quantities block in the beginning. We cannot declare variables after any equation. And we have the counterfactual plot for fixed age, and I set these data to prediction mu1 and prediction y1. And then we have the counterfactual plot when we fix the marriage rate, and I set these data to prediction mu2 and prediction y2. And the original prediction, I named them to prediction mu3 and prediction y3. And these will also be useful at the next plot, so I keep them. And then we can calculate the values one by one. So for when age is fixed, we set beta A times 0. And when marriage rate is fixed, and we let beta m times 0. And for the other part, beta m just times counterfactual m we provide. And in this case, beta A times the counterfactual A we provide. We passed the model we've written here and fit the model 5.3 again using the new data. Here we have a new vector of data called counterfactual A and new counterfactual M, and they are the same data from -3 to +3 with a length of 50. And then we can plot the results as usual. Firstly, we can plot the counterfactual plot when age is fixed to see the impact of marriage rate on divorce rate. We select the prediction mu1 and prediction y1 from the posterior 5.3 and use the result to calculate the confidence interval and prediction intervals. And then we can use the line plot and ribbon plot to visualize the result. You can see that marriage rate have a little impact on divorce rate when age is set to be 0. So we arrive at the same conclusion as the result in predictor residual plot here. To see the impact of age, we follow the same logic. So here we choose prediction mu2 and prediction y2 and plot the same figure, and we can see that marriage rate is negatively related with divorce rate. The counterfactual plot seems to be the perfect visualization tool for multiple regression, right? The author warned us that the plot shows the prediction of any combination of our independent variables. However, some of these combinations may be even impossible in the real world. For example, it's highly possible that you can't find a place where the median marriage age at 2 while the marriage rate will be 0. So the prediction on this area will be highly unreliable. In the counterfactual plot, you cannot tell which points are more reliable while other points are not. Also, we can visualize the result using posterior prediction plot. In simple linear regression, we can use the training data to do a backtest. However, since we have more than one predictors, we cannot easily compare the prediction value and the predictors just like we did in previous chapter, where we plot our predictors on the x-axis and plot the prediction on the y-axis. Instead, we will plot the prediction values against the true values with the same predictor value. So the points closer to the diagonal line here with slope equal to 1 will be a better prediction. And here are the codes to draw the plot. Firstly, we still need to select the prediction mu value and prediction y value from posterior 5.3, and then calculate the confidence interval and prediction interval bounds from the result. We need the points, which are the true value and the predict value. And then we need a diagonal line. Instead of using a geometric line plot, we can use the geometric AB line function. So in the geometric AB line function, you just need to input the slope and the intercept value. And the diagonal line will have intercept equal to 0 and slope equal to 1. The line type to be dashed and the alpha value to be 0.7 to make it more beautiful. The last thing we have to do is to plot the prediction intervals and confidence interval. So unlike what we did in chapter 4, our prediction interval and confidence interval will not be a region or an area plot. Instead, it will be lines of different lengths and on the point. The function that can help us plot these kind of things are geometric segment. In the geometric segment function, the aesthetics have 4 components: the x, xn, y, and yn. Geometric segment function will draw a line from the point of xy to the other point xn, yn. The lines we are going to plot are vertical, so the x and xn values are the same, and the y values and yn values will be the lower and upper bound of the intervals. Can be written as a geometric segment with aesthetic x equal to true y and xn equal to true y as well. Yu can be equal to lower bound of confidence interval while yn being the upper bound of confidence interval. For prediction intervals, we just do the same thing and replace ci lower and ci upper to pi lower and pi upper. And I also set different alpha value for prediction intervals so that we can distinguish pi and ci more easily. So here is the result. Finally, we can get into the second section of tutorial chapter 5. In the second section, we are going to learn about how to code categorical variables in a STEM model. And instead of using dummy variables like we have learned in previous statistics class, instead we will prefer index coding to dummy coding. There are 2 advantages of using index coding over dummy coding. For example, in this case, we want to add gender into our model, and if we use dummy coding, we may say a female to reference level, and that female being 0 and male being 1. So the parameter of this male value will be actually the difference between female and male. So what's the problem here? So for the prediction of female, we only need beta times weight, but for the prediction of male, we have male plus beta times weight. Notice that male and beta both have their distributions. So the prediction for male data will be influenced by the variance in the male parameter and the variance in beta parameter. But for the female predictions, it will only be impacted by the variance in beta parameter. On the other hand, in index coding, we will have 2 intercepts, one for male data and the other for female data. This way, male and female predictions will have the same amount of variation. The second advantage will be more obvious if we have more than 2 levels in the categorical variable. In the next example, the categorical variable will have 4 different levels. And if we use dummy coding, we need to create 3 dummy columns, and we also need to estimate the intercept one by one. However, if we use index coding, actually we don't need to change our data, and we can use one vector of length 4 to do the estimation. We will come back to this example later, and for now, let's go to our height example. This is the same example we use in our simple linear regression model, where we want to know the relationship between height and weight. But here we add one more variable, gender. So you can see this is the original simple linear regression model we used in chapter 4. Let's see what we need to do to modify it for the additional categorical variable. Firstly, in the data part, we need a new integer L indicating how many levels are in the category. And then we need a new variable called gender with length n. And notice that you must set the gender variable to integer, or any categorical variable must be in the form of integer. If you set it to a vector, Stan will treat it as floating number. In the parameters block, the only thing we need to change is the alpha. So now we want to have 2 alpha values, one for male, one for female. So the L we've declared can be used here, like how many levels of category will be how many alpha values we want to estimate. And actually you can store alpha value either in the form of real array or vector. Either one should be fine. For the prior setting, we don't need to change anything, even though the alpha now is a real array, not a single real value. The sampling function, sampling statement here still supports this real array, but the likelihood need to be changed. So the gender data input in our STEM model will be like 1, 2, 1, 1, 2, 1, something like this, where 1 suggesting male and 2 is female. We can use these different gender values to access the different element in the alpha array. For the ith row of data, the alpha value should be the gender of the ith row, and the weight should be the weight value in the ith row. And we can use a for loop to iterate through all the rows in the data. If you think this long calculation is too long, and we can set another variable called mu, and mu I, this is just the mu I value, and we can put the mu I value here. If you want to do this, don't forget to declare the mu value in the beginning of the model block. In the generated block, we also need to change this mu to something like we did here. So the mu value is calculated as what we did in the model block, and for prediction of the height value, we use the normal RNG function, and also inside the for loop, since the mu value will be changed in a different iteration. Okay, and we can go back to our studio to input our data, and notice that the gender here, I set it to the height data of male and +1, because originally the gender data is 0 and 1, but in RStan or in R, the first element of a vector starts at 1, not like Python where we starts at 0. So I made it 1, 2, 1, 2 instead of 0, 1, 0, 1. So here I print the numerical results, and we can see that there are 2 alpha values, where alpha 1 is the female intercept and alpha 2 is the male intercept. And actually there's no big difference for the mean value. Then we can go to the exercise where we have more than 2 levels in the categorical variable. So in this milk data, there are 4 different kind of clades. I don't know what a clade means, but yeah. So, and what we need to do on our code? Actually, not much. You can see that we keep the integer n, where the number of rows, and L indicating number of levels. We just need to change the weight to mass. This is the X in the model, and the Y to 1,000 calories, and gender to clade. And then the alpha values will still be length of L, and in this case, we will actually have 4 different levels. For the model block, we don't need to change anything. We just need to replace the name of x value and y value. And the prior are exactly the same with different prior values. And for the generated quantities block, we didn't change anything as well. And for data inputting, here, the original data is in different name, and we can use the as integer function to convert these names into integers, like 4231, like this. And you can see from the result that we have 4 different intercept values, and with very small modification on the original STEM model. So this is the advantage of using index coding over dummy coding. Imagine if you are using dummy coding, you will have some problems in the data input part. You will need to create extra 3 columns to store the dummy variables. But if you use index coding, everything is just fine. So this is the end of tutorial chapter 5. I hope you enjoyed the video. And don't forget to use index coding on your homework. In the first version of the textbook, the author actually used ARMY coding, but in the second version, the author switched to index coding, which is a great improvement.